Hello everyone. In the previous session, we studied about the basic configurations and characterizing amplifiers. So now in this session, we'll study about the common source amplifier and which is also called grounded source. Otherwise, grounded source because the source terminal is grounded, and common because the source terminal is common to both input and output side of the configuration. So now this is the configuration of the common source amplifier. You can see here this V signal is the input source with the internal resistance of R signal, and this coupling capacitor CC1 at the input side and the CC2 at the output side. Here the drain terminal is coupled to the load resistor through this coupling capacitor CC2. Both these coupling capacitor will block the DC signals and allow only AC signals to pass. And here we have a capacitor CS, which is of high value, usually in the range of microfarad, which will protect this current source and it acts as a short circuit. So now we'll go through all those things in detail in the upcoming slides. So now this is about the configuration of the common source amplifier, and here this is the small signal model of the common source amplifier. You can see that the capacitors are short circuited. See here, this capacitor is short circuited. This CC2 is also replaced by a short circuit. And here this is the internal block diagram of the MOSFET. You can see here VGS. This VGS is portrayed here, and this GM into VGS is the current source, and this R0 is the output resistance of the MOSFET, and RD we have written it here, and RL is over here. And when I look from this side, this resistor is RG here, and whenever I look from this side, I will get the value of the resistance R in, and whenever I look from this side, we will get the output resistance R out. Okay, this much you need to remember. And this IG current into this MOSFET is equal to 0 because this gate resistance is very high. And yeah, as I mentioned earlier, this capacitance CS, which is connected between the source and the ground terminal, is of very large value in the range of microfarad. It will provide a small impedance which is almost equal to zero impedance, and it acts as a short circuit at all frequencies of interest, and any signal that passes through this CS capacitor to ground will bypass the output resistance of the current source. Hence, this capacitor is also known as bypass capacitor. And we know that for any capacitor, the reactance is given by XC is equal to 1 by 2 pi FC. So, as and when the frequency is becoming lower, the capacitor's efficiency will also become very less. So since this F is in the denominator, if it increases, the value of XC reduces. If the F decreases, the value of XC increases. So like that, it is inversely proportional. And this, I mentioned it earlier, this capacitance is acting as a short circuit. So in order to analyze this circuitry, we will assume that this capacitor CS will act as a perfect short circuit. Okay, and then This is about the coupling capacitor CC1 and CC2. CC1 is at the input side and CC2 is at the output side. It blocks the DC signals and it allows only AC signals. That is about this coupling capacitor CC1 and CC2. And this as frequency decreases, effectiveness of capacitor also decreases. Just analyze this formula, you will come to know that. And one thing you must remember here is that the RL that is here, it can be the load resistance of this stage, or it can be the input load resistance of the next stage, if so any stage is present over here. If it is cascaded, the RL can be the input resistance to the of the next stage, if there is any stage. Otherwise, this RL is the load resistance of this stage itself. So that is about RL. And next, this is the analyzing part of the circuit. See, at the input, we know that this Ig is equal to 0 because Rg is very high, and this Rin, see, we are looking from this side, isn't it? So here we will, this is the Rin value. So here we have Rg. So this Rin is equal to Rg, and that is written over here. Next, Vi is equal to Vsig into Rn by Rin plus Rsig. So how did we get this? See here, Vi is the voltage over here. Okay, this Vi is equal to the voltage across this terminal is Vsig, isn't it? Into the resistance across it is Rsig, isn't it? So Vsig into Rsig divided by, Vsig into Rg divided by Rsig plus Rg. So Vi is equal to V signal into Rg divided by R signal plus Rg. So that is this equation that is written over here. Okay, now because Rn is equal to Rg, I'll substitute Rg for Rn. So we'll be getting this equation. Next, this Rg, R signal, is selected very large such that this R signal is much greater than Rg. So this Rg plus R signal will almost be equal to Rg, isn't it? So now this Rg and the Rg that is present in the numerator will get cancelled. So Vi will be equal to V signal, isn't it? So Vi is almost equal to V signal when R signal is much greater than Rg. So here this should be reversed. There is a small mistake. Rg should be greater than R signal should be greater than Rg. So I'll make that correction and send the notes to you. Don't worry about it. And now this Vi is almost equal to Vsig. So this is one conclusion we drew from this equation. Now this Vgs is equal to Vi. This Vgs, here we have Vgs, isn't it? Here we have Vgs, here Vi. This Vi is equal to Vgs. So that is written here. And the output voltage is equal to general formula of voltage. What is it? I into R, isn't it? So here we have the current, that is Gm into Vgs, and here we have the resistances that is connected in parallel, that is R0, Rd and RL. Parallel combination of R0, Rd and RL will form one set of resistor, isn't it? So output voltage is equal to Gm into Vgs into parallel combination of these three resistances. So since the current direction is opposite, minus symbol is inculcated in this formula. See here, V0 is equal to this current into resistance, I into R. Negative because the current direction is opposite. Gm into Vgs into parallel combination of R0, Rd and RL. And voltage gain, we know that voltage gain is equal to output voltage by input voltage, isn't it? So this output voltage equation is here, and input voltage Vi is equal to VGS, isn't it? So V naught by VGS we are supposed to do. The VGS in the numerator and the denominator will get cancelled. Okay, so this voltage gain will be equal to minus GM into parallel combination of these three resistances, that is R0, RD and RL. Next, output circuit voltage gain. Whenever we talk about output circuit voltage gain, remember this load resistance will not be there. This load resistance will be absent. So I'll repeat it once again. Whenever we talk about output circuit voltage gain, RL should be removed. So the output circuit voltage gain is indicated or denoted by AV naught, that is equal to minus GM. Since we don't have RL, I'll not be writing RL. It's as simple as that, into R naught parallel RD. So remember, voltage gain is denoted by AV. Open circuit voltage gain is denoted by AV naught. Remember this. RL will be absent. And now the overall circuit voltage gain, meaning overall meaning from this signal source to the load, overall circuit gain, that is given by Rin plus R signal into AV, this AV. Okay, so Rin is equal to Rg, isn't it? So we'll substitute Rg for Rin and we'll get this equation, and GM, I'll substitute the value of AV. So GM into parallel combination of these three resistances, and this minus symbol is written over here. So this is overall voltage gain. Okay, and in order to determine the output resistance, what we do is we set the V signal to 0, meaning the signal generator, that is at the input side, V signal is replaced with a short circuit, and now this R out will be equal to R naught parallel RD. R naught parallel RD. This load resistance also will not be there. This is about the common source amplifier. Okay. And in the next session, we'll study about common source amplifier with source resistance.